So we're going to go over problem one. So with problem one, it asks us to implement the SARSA, which is an on-policy reinforcement learning algorithm. And that just stands for SARSA stands for State Action Reward State Action. And so with that algorithm, we're going to use to solve the Quinton's rule problem. So briefly, this is what the Quinton's rule problem looks like. This is the start state that the agent is going to be placed on, and it's going to try to navigate through this 10 by 10 grid to get to the yellow state. The yellow state it's the gold state. And so this red blocks basically the walls. We can't let the agent run into that. It will get deducted points. And the point of this is to use reinforcement. So going briefly back to the code, so essentially, before I even explain, I kind of explain a little bit of what SARS is. And so, like I mentioned, it's an on-policy learning algorithm. And so the whole point of that algorithm is to get the agent to learn the value of the policy and then actually follow it. So we're going to be using called Epsilon Griddy. And this function that I created, it takes in two values, an action value and epsilon. And so basically the aim of this function is to get the agent's selected action and use that policy and then get the value from that action and then return the agent's action index of that. So that's what this function does. Now we're moving on to this other function I just defined. This is the algorithm, and so it requires these parameters. It requires the environment, it requires the alpha, and that's just for essentially that's the learning rate, and then gamma is the discount factor. Epsilon is like the probability of the epsilon Griddy function, and then this is just the number of episodes. So the idea of this function, it's supposed to take in those parameters that I mentioned. So remember the E is the env is the environment in sense of the Quinton's world. And basically we're going to return the Q. So you'll see in the bottom, we're returning Q, which is like the learn state action value function, while the reward sum is just a list of total rewards that gets accumulated for each section, for each episode. And so the idea of this is basically we are calling this SARSA algorithm, and we do it from this part. So first we initialize the environment, and then we call on the SARS function, and then this is us plotting it. So we're going to briefly explain what this does. So like I said, the Q is the state action value function, and we wanted to we use NumPy, taking those two, the state and the action, and then we have this empty rewarded array, and it gets added later to it. And so for each episode, we are going to first get the state. This is the initial state, first time runs. Then the action of the epsilon Griddy takes in the state and the epsilon, and then the total reward is 0. So this true statement, the idea of this guy, it goes right here, it's essentially for each episode, it runs for each episode until it stops, until like literally there is no state. So it gets the next state and the reward and gets the outcome of it. And we pass, there's a function in the environment file. We pass in the state and action, and that's what we set the next state and action to in the reward. And then the total reward gets updated from this. And then, so this is the case if the next state is none. So if there isn't a next state, then just go ahead and get the target reward, set it to the reward, the target set it to reward, the hour just set to the target minus the Quinn state that takes in the action, the state and the action. And then that just gets updated with this is the formula that we had to use for the epsilon Griddy. And then we break out a loop when there is no next state. But when there is a next state, this is the formula that we were using. That one, uh, we use the epsilon gradient, get the store the next state. We're passing the next state, the epsilon, and then update that to be the next action. Target is this is the formula that was given in class, the error was given in class, and then this is us updating the state and the action. And this is getting our next state and our next action, and then it just keeps going until we get no state for the next one. So then we get these four graphs. So for this first graph, this top left one, each dot represents like the learned Q value of action in a specific state. So the R is stands for like the right, U is upper, L is left, D is down. And so the x-axis is the state numbers that range from 0 to basically 99. Since Quentin's world is 10 by 10, so that's 100 states. 0 through 99 is 100. And then the y-axis represents like the Q values. So basically, this graph right here just shows that early in the training, most of the Q values are near 0, reflecting the agent's initial uncertainty about what route to take. So basically, over time, the certain action in a specific state begin to stand out with higher values, indicating that the agent actually has learned which moves are more rewarding. So when it gets to negative Q values, it represents penalty states. So like the red zone, remember that red wall that I showed you? And so that's when the policy begins to form and the action values start just to be different across all states. And that ultimately leads to the agent to prefer a specific action based on its expected long term rewards. So it's going to pick a specific action because it wanted the high yield rewards, aka the Q values. The Q values. So that's for the top left. So this top right graph basically, this just simply shows the grid layout of the Quentin's world, which kind of just shows it. This is just visually summarizes the agent's decision-making policy after training. So each arrow just shows like the best action from that specific state. So over time, the agent just learns how to move around without hitting the red walls, and eventually gets to the yellow target, the yellow state. Now, more specifically, the graph just shows just indicating like what's the best action to take in each state. And so like for example in this one, for this state I showed you, it prefers the down state, the down action for that because it's the most rewarding. So it basically shows that each arrow points in the direction of the highest value action based on the learned Q values. So either up, down, left, or right, depending. In that case, what I just showed you, it's down. So basically, over time, the agent just explores and learns from its environment, and the arrows begin to form a clear path just from the green star state to the yellow state. And so, of course, ultimately, we're trying to avoid the red wall. Now, this bottom this bottom left graph, the point of this one is just to show the total reward the agent earned in each episode during that training. And so the x-axis represents the number of episodes, while the y-axis represents the reward value. There will be about like 500 episodes because that's what I set it to. And the rewards just range from negative, basically, this case, negative 2.5 to 1. A little past negative 2.5, like negative 2.75, I would say. Yeah, so, but what about this graph is that it basically illustrates how the agent performs, and it shows that it actually performs pretty well throughout the training because there's an upward trend that indicates like the agent is learning. And initially, the agent kind of didn't do well. It starts off in a given state, but then moves, throughout the environment by taking a course of actions. And, each action can either yield like a reward or a penalty, just depends on the agent when progressing towards like the goal, or is it hitting like the red walls or obstacles. So those rewards are actually updated so these rewards are actually used to like update the agent's like Q values, which guides them through future decisions. So you can see like early on in the episode, the agent explores more and it's often like getting negative rewards, which is why you see around like 10 episodes it's getting hit like really like a negative total reward, and that's just it's exploring. So as you can see, the as the training continues, the agent learns to avoid the penalties and reach the goal more efficiently, but eventually the reward stables around +1, and which kind of just shows that the agent has actually learned and it kept up with the policy with making minimal mistakes. This last graph right here on the bottom right just is a heat map that just shows the just shows it the visualize maximum Q values for each state across all actions. So basically each cell represents one state of the Quentin's world, and the color just tells us how rewarding that state is. And as you can see, the lighter colors, just based on this scale right here, the lighter color stands for a higher value, while the darker color stands for a lower value. Okay, great, but what does that show? Well, basically, this bottom right graph shows the maximum learn values for each possible state in the environment. So, as mentioned, the lighter colors just represent the higher values, while it typically, um, which basically means getting closer to the goal. But if it's a dark cell, that just shows it's like a lower value state. Which what does that mean? It means that it's hitting the penalties and or it's just not progressing further to the goal. So basically, according to the graph, over time the agent learns where the areas are most rewarding, and it kind of shows like the best route throughout the path, throughout the environment. So yeah, that is pretty much for problem 1. I'm going to be going over problem 2. So essentially, with problem 2, we are implementing this model-based reinforcement learning algorithm called Dynamic Q. And the idea of this problem is that we're using that algorithm to solve the cliff world problem, which is a 4 by 10 grid environment. And the agent, I'll just show you what the picture looks like. So this is the start of where the agent goes, and that's the goal, and the idea is to avoid the cliff. It doesn't want to fall off the cliff. If it does, like it's negative points, and it's going to learn not to do that. So essentially, we're trying to get them to avoid the cliff area from between the start and the goal. And so a little bit about like the dynamic Q, it combines like the model free Q learning with the model based planning. So the agent actually learns from its experiences and also uses it uses a learned model to simulate the additional experiences and update the value function. So what I did in this code is basically we use in this case epsilon gritty, just like how we did before. Pretty much the same thing here, it's explained. So yeah, pretty much the same here. So essentially here we just kind of connected the two, where we just initialized the cliffworld environment from the environment file, and then these are the parameters that we had to give for the Q dynamic hyperparameters. Epsilon is the exploration rate, alpha is just the learning rate, gamma is the discount factor, and then the number of planning steps is k. So in this case we just set the number of steps just 500 and the maximum steps 1,000. And so here's what we're actually calling the environment, and this is actually learn environment function. That's gets it updates the Q value, the reward sum, and the steps per episode. And so this learn underscore func environment that comes from the RL file, which uses the dynamic Q. And so this is us just graphing it. So basically, if before we even start, right, we're gonna basically the environment details, it includes like the grid is a 4 by 10, so there's only 40 states in this problem. The other one had a lot more. This one only has the start state's going to start at 0 and the goal state it's 9. So we're trying to avoid the cliff region, and we don't want it to take the wrong steps leading, um, which will lead to a state 0 and with a negative 100 penalty. So it can only go right, up, left, and down. Same actions as the previous problem. So basically, we're just trying to get the agent to learn a safe path to avoid the cliff and reach the goal. And so we're going to keep doing this by repeating the episodes and simulating planning for dynamic Q, just so the dynamic Q algorithm can help the agent to learn it more efficiently than using like a standard model free method. So basically, let's just dive into what the these graphs mean. So for the top left graph, each dot represents like the learned Q value action in a specific state. So like I said, I already mentioned what RULD are. Those are just the actions that the agent can take, which is right, upper, left, and down. And the x-axis is the statement of numbers that range from like 0 to 39, which we know because the Cliff World grid is 4 by 10, and the y-axis represents the Q values. And so if you just take a look at this graph, the graph has a sharp negative values when the agent goes down from like 10 to 18 to state 10 to state 18, and that just shows that the agent um, earned a negative value, and then it also earned a negative value when it went to the right at the very start. So what does that mean? Well, basically, when the agent moved downward between the states 10 to 18, it got a Q value that was really negative, and that's because again the agent went to the edge of the cliff in those states. So that just leads to like a large penalty. So that's what happens when you go straight down, or if it makes right at the early start. So, but I mean, you can tell from this graph that as training progresses, the agent actually learns to avoid those action that causes such like a large negative reward. So if the agent avoids moving down in that region, it actually receives a smaller negative value. So um, yeah, it was just receiving like a smaller negative value, which is great. But over time, you can tell that the agent actually learned to steer clear off the cliff. And high values in the graph is just indicates that the agent actually has developed some confidence in those certain areas. And you can tell that the lines actually stabilize across the state. So overall, for this graph, it demonstrates that the agent has learned which actions yield higher rewards and which to avoid, such as those getting into the cliff. So, going to the top right, this one, similar to the last graph, basically, this just shows like the 2D layout, the cliff world problems, where each cell represents the state of the environment. So, inside of those, in each of those cells, there's an arrow that indicates the action of the highest Q value. So basically, the point of this graph is to just to show that the agent successfully learned the policy after training, since each arrow represents the best action to take in the given state. So the agent can actually, you can just tell right there, the agent was able to form a clear path from the start of the state to the goal of the state while avoiding the cliff. So instead of like moving directly towards the goal, you kind of notice that the agent finds moving along the top of the grid is much safer, which I mean is great because it's just not near the cliff, and the cliff's at the bottom of the grid. So for this bottom left graph, the graph shows that the how the agent performs throughout the training process. So basically, each point corresponds to the total cumulative reward as it progresses to the goal state. The x-axis just represents the number of episodes, while the y-axis represents the total rewards. But okay, so like what about that state or that graph? It just shows that the agent performs throughout the training process in the beginning and the total rewards are low, but they gradually increase. So that's good because that just shows that the agent was learning. But not only was it increasing, but it was more consistent over time. So again, this just suggests that the agent was at first right here was falling off the cliff pretty often and it was getting a large penalties. However, after like a couple of episodes, like around like 30 episodes, the agent learns to learn the agent begins to learn how to avoid the cliff and reach the goal much more effectively. So as the training progresses, the rewards improve, reflecting a better performance. Yeah. So basically, overall, you can tell that it's experiencing like an upward trend in the graph, which just indicates that the agent was successful and learned how to reach the goal state without actually falling off the cliff, which is great. So for this last graph here, um, it's just a heat map that visualizes the maximum Q value for each state across all possible states. So each cell represents one state in the cliff world, and the color tells us how rewarding the state is. So, like the lighter the color, you can tell that it's a less of a negative number, which basically means a higher Q value. And then the darker the number just stands for like the more negative, aka the lower the Q value. So basically, what does that mean? It just shows like the maximum, Q value for each state. It just represents by color. I mean, like I said, the lighter color, you know, gets higher Q values, while the darker color is lower Q values. So to get the lighter color, you need to gain reward, and then get a darker color, you're getting penalties or not making much progress. So in the gist of this, according to the graph, over time the agent actually learns which areas the environment are more rewarding or most rewarding. And the brighter regions are highlight the states of the agent that is like the most safest routes to go to get to the end value. So yeah, that is it for problem 2.